Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let's start with the session, and Till is going to give a talk about ticks and graph drawing. My PhD students were very eager to hear about that paper, so I'm now eager to hear about it.
Yes, thank you. And let's see whether this works okay. Yes, so thanks everyone, and hello everyone. Graph drawing in ticks, that's something I want to talk about. Graph drawing in ticks tries to address a problem that most of you, or perhaps every one of you has had, namely when you prepare a paper that is on graph drawing, because then it's going to contain a drawing of a graph. And it turns out that's not so easy to get right. And just to show you an example, this is something I took from last year's conference proceedings, more or less randomly. I mean, all of the papers contain drawing of graphs. And I think these are pretty nice drawings. And when you have a very close look at it, you'll notice some things. For instance, in this drawing, you have some font of the main text. This is a typical TeX document, so this is computer modern, whereas in the drawing itself, you have a sans serif font. You'll also notice that the math stuff isn't that great because the tool, I mean, this H prime doesn't look that great. Also, the size of the font kind of differs from the main text. It also turns out that the arrow tips are different, and this is all inside one picture. So inside one paper, so by the same authors. Now, this is very typical. This is something that happens a lot of times, and there's a reason for that. And the reason for that is that two worlds sort of collide. And on the one side, we have the world all of you are familiar with, namely the world of graph drawing software. So graph drawing software, say GraphWiz, what you do is you specify a graph, and then you run GraphWiz, and what it produces is a great layout. I think this is the perfect way to draw this particular tree. But as you also notice, when it comes to things like mathematical stuff inside a node or so, it's not that great. And this is something that most of the software will suffer because graph drawing software is geared up at computing good layouts. Now, on the other hand, we have another world, named the world of typesetting, TeX in this case. And TeX is certainly really great at producing things like integrals on 2π. Also, as you'll notice, these days TeX comes with graphics packages, and they are great at producing, say, having the same colors as the main document, stuff like that. But I mean, TeX is not a graph drawing software, so when it comes to computing a layout, it does something, but it certainly doesn't look good. What you really want is that. So you want the layout that is as good as what your graph drawing software does, but you want the whole power of TeX and graphics package that allows you to draw the nodes in this particular case. Now, this is a real problem, and to get there, and graph drawing in ticks is one possible solution to that. So there are other ways to do this, but here what is done is you take an existing document description language, in this case TeX, you could use other ones, and you take an embedded graphics description language, in this case ticks. Now I'm going to talk more about ticks in a moment, but so the point is you take an existing system that is good at doing typesetting, and then the idea is you add something, some syntactic extensions, some options that allow you to specify graphs easily, and then do the whole graph drawing, not in a separate software, but really as part of this document processing. And if you do it, I'm going to show you in more detail how that works. What happens is that, first of all, because now TeX is running the whole thing, nodes and edges, all the styling stuff is going to be exactly the same as in the main document. What's also going to happen that the graph drawing algorithms will profit from the fact that TeX knows very well how large your boxes are, what the exact sizes are, stuff like that. And they are no longer an external program, so the workflow is pretty fast. You just write it as part of your TeX document, and the graphs will directly be put in there. And another aim of this whole thing is, now, if you want to implement a new algorithm, you can sort of concentrate on the algorithmic aspects, because this whole framework, all this styling stuff and how to draw it and computing size, all that is completely taken care of by the framework, and you sort of focus on the algorithmic aspects. So this is sort of the promise behind this. Now, in the following, I want to show you three things. First of all, how do I use it? So how do I use this graph drawing in TICS to draw a graph? And then I'm going to talk a little bit about the magic behind it, so how is that implemented. And then, so suppose you have a new graph drawing algorithm, and in this conference I saw lots of them. So suppose you want to implement that, what do you have to do? And I'm going to show you a very tiny but complete example of what you would have to do. Okay, so that's the idea. But first let me show you a little bit on how to use this. Now, graph drawing in TICS, I presume not everyone knows what TICS is. So here's my two-slide introduction to this. The idea is, well, you have a TeX document, and somewhere you say use package TICS, so somewhere at the beginning. And when you do that, a large package of TeX macros gets loaded, and a new command becomes available called \TICS. And now what you can say is something, in the middle of your TeX document, when you TeX it, this is going to come out of it. And as you can see here, it says, well, I want to fill a red something. Well, somewhere at some origin there should be a circle, and the radius should be half an EX height. That's TeX speak for the height of an X character. And because the radius is half of it, we are going to get something that is as high as a normal X character. Okay, now what TICS does is it scans this thing, and then TeX does lots and lots of parsing and transformations. At the end, you get very low-level primitives for producing PDF if you want PDF, or PostScript if you use normal LaTeX, or even SVG if you want certain versions of TeX. So whatever you want, that is directly produced while TeX is running. Okay, so that's TICS on one slide. Now, what is going to be important for this talk is that TICS also has certain support for nodes and edges. I mean, this is about graph drawing. And this is what TICS does. You can say, hey, I want a node, let's call it A, at a certain position on the page. And it should say hello there, and has a shape called rounded rectangle, and another node that has a tape shape, and a circle, and a diamond, and so on. And then there's a certain syntax to add edges between all of these guys. Okay, so this is what the package can do. All of this is implemented in TeX. And now the point is graph drawing. Well, graph drawing is all about getting rid of this at stuff. So we no longer want to specify coordinates by hand, which takes a long time and it's very hard to get if the graph gets bigger. And this is what graph drawing in TICS offers. Use this. So you can now say, hey, I want to load a new library called graph drawing, essentially. And then a new option sort of pops up called layered layout. And what it does, you just add it, and then you get rid of all the at, so you're no longer allowed, or you shouldn't specify any longer where the nodes should go, because this is now the job of this particular option. When you run it, well, it's going to run, in this case, the Sugiyama method for computing a layout for these guys, and it's going to look like this, essentially. And if you, instead of layered layout, use another option, say a spring layout, then well, what's going to happen is you get this typical spring layout, because now spring layout will be run in the background, and you can configure these to death with things like node distance and all sorts of other things that you can specify that will be taken into account for drawing these graphs. Okay, so this is basically what you do as a user to use all of this. And before I continue and show you how all of this works, I would also like to talk a little bit about syntax. And the point is that all of this graph drawing in TICS is aimed at human beings, mostly, who want to simply write down a little bit of code to get a graph drawing like this inside their TeX document. Now, why do people use TeX? In case you wonder about that, I mean, it's not such a great language at first sight. But the point is, when you want something like, say, c squared, what you have to write down is $c hat $2, and that's it. It takes about a second. If you want to do the same thing, say, using Word, then you have to open the formula editor and then do lots of clicking. It takes a long time. It's really fast to write this down because it's very concise. So what is great about TeX is the concise syntax. And what you can see here, that's not particularly concise. I mean, it takes a lot of space to specify a simple graph. And because of that, turned out to really make graph drawing in TeX useful, we need a new syntax. And so what the system comes with is this. So I had a look at the different syntax available, and in order to specify by hand, the chosen syntax, well, basically is based on dot, because the dot notation used in GraphViz, that's much more concise, much more easily to use. And it turns out that the way the parsers work, it's hard to parse dot as is with all it does. So the real syntax is a little bit a mixture of the philosophies of dot and whatever Tix does. But if you have a simple dot text like this one, then it's going to work exactly the same you expect. You know, hello world, C dollar, C squared, delta, and so on. And let me just spend one slide on perhaps the differences between the normal dot and what this syntax now does. So the key features, first of all, you can suffix all your nodes simply in square brackets by options that you want to add. So a hello node, a tape node, a world node, as before. So in order to get this drawing we had earlier, you write down this now. Another interesting thing is, which I kind of prefer over what dot does, is that you can add edge options following the edges. So you say, well, I want this edge from world to delta. Now it should be dashed and it should be blue. So you just add it at the edge. And another edge from delta to hello should bend a little bit to the right and should have some text on it. Yeah, stuff like that. What's also interesting, there are two additional edge kinds. So a backward edge and a bidirectional edge. And the rationale for that is, we had a talk earlier, actually yesterday, where it was pointed out that if you want to do cycle removal, it's good to know which edges you have to, which arrows have to be put in the other direction. And this backward edge is, sort of communicates to the algorithm that it would be a good idea that to reverse this one in the final output. Okay, and finally, because this is, again, for people who want to draw graphs directly inside Tech, there's also good support for trees because they are pretty important. So you can say, I have a root, well, it has a left child and a right child. The left child has 1 and 2 children. The right one, well, it has one child that has no left child, but a right child, and then say it's a binary tree layout, and you get something like this. Okay, so there's more to the syntax, but at this point I'm going to stop this and spend the rest of the time to show you a little bit on not how you use it, but how it works, and then how you implement new algorithms. So yeah, graph drawing in Tix. Well, Tech is really a great program, but implementing any sort of advanced algorithm is absolutely impossible directly in Tech because it's Turing complete, but that's about it. So if you want to do something grand like the Sugiyama method, you won't be able to program this in Tech. However, there's hope because there's another language called Lua, which is small, simple, elegant, nice functional language. And that has been integrated into modern versions of Tech. Now, most of you will actually be using Lua Tech without noticing because it's really moving in that direction. Just click on Tech. What happens, Lua Tech is run, and that's because all it does is essentially offer this one new command. So Lua Tech comes with a command called /direct Lua. And when a Tech document just, when it encounters direct Lua, what happens is that Tech sort of stops, handles over control to this Lua kernel, which is about 40 kilobytes, so it's very, very tiny. And what it does, well, as you can see here, this looks like normal program code, more or less. We have a sum, then a for loop from 1 to 100. We add up these numbers. And then tech.print means, OK, whatever comes out, we turn it back to the tech stream. So, and this is, if you run this via normal tech, you're going to get this output. And this is really much nicer to program because try to do the same thing in Tech. It's possible, but you have to really know how to do this. OK, now this direct Lua option is really what's behind this whole graph drawing thing, and let's say how a graph is drawn. So let's have a look. So on this Tix layer, you say, well, I want a graph with a tree layout. And this tree layout option, all it does essentially is trigger a call using direct Lua to something called begin graph drawing scope. So it calls this framework. And then at that point, when we see A to B to C, we're going to create, now Tix is going to create 3 nodes with all this nice, it's going to render them, put a shadow behind them, whatever. But instead of inserting them into the page at that point, instead we again use direct Lua to add the nodes on this lower layer. And that continues until the graph is done. And then we get a call to run graph drawing algorithm, again using direct Lua. At that point, sort of on this Lua layer, a object-oriented description of the graph will have accumulated there. And then we load and run the algorithm. And as you can see, all of that happens on the Lua layer. So here you do not have to worry about TeX at all. And these algorithms, I'm going to show you in a second, they don't see TeX. What they see is an object-oriented model of a graph. So they run, and then they compute new positions, and then at the end, graph drawing scope, they use sort of callbacks to tell TeX, now I know, please place the node you have pre-computed there on the page. And then this is what you see what comes out of it. So in order to implement a new algorithm, what you need to do is go into this load an algorithm and run it. And this is what the framework does for you, so what do I have to do? And yeah, so how does that work? Well, the idea behind this is to treat graph drawing as, which is very traditional, what other systems also do, to treat it as a transformation starting with some graph, and then you transform it, transform it, transform it, transform it, and at the end you have a drawn graph. So this is what happens. And TeX really follows this philosophy, because if you have a new algorithm, you sort of declare, okay, my algorithm, well, it wants a tree. Now, if the input isn't a tree, then the framework is going to make sure it is. So if you feed in a click, then a spanning tree will be computed, and the algorithm is only going to see that. Then it does something with it, and it can also say at the end, okay, now I'm done, but then the framework will continue to transform it further until we have the drawn graph. And I'm going to show you this on one complete graph drawing algorithm. So this is what you would really have to write down. This is an algorithm that is going to place nodes on a circle. So something very, very simple. It has to fit on one slide. But let's have a look at what happens. So you create a new file called, say, very simple demo.lua, because it's written in Lua. And then you start with something like graph drawing new algorithm class. So I want a new algorithm. And it has one property, works only on connected graphs. So because of that property, the framework knows that it's only going to feed connected graphs into that algorithm, namely into this run method. Now, if the graph is not connected, the framework will decompose it and then run it on the different components. Well, now, I don't want to go into all the details, but essentially you have the graph object here. You can read the radius from whatever the user configured. Then you have an angle alpha, which is, well, 2 pi divided by the number of vertices. This is Lua speak for iterating over all the vertices. And essentially, well, the vertex position, the x and y position, get the cosine and cosine. So they're going to be placed on a circle. And then there are some quirks of Lua. So this is what we put. This is a complete graph drawing algorithm. You put it in some file. And the moment you do that, what you can do next is use it. Namely like this. You say TeX graph. And I want a layout equals very simple demo. That's the name of the file. And this is going to come out of it. So this is really what I did here with a radius of 1 centimeter. Let's have a look. This is the specification of the graph and that syntax. And as you can see, if you have a close look at it, this is not a connected graph. So because we said works only on connected graphs, it was decomposed by the framework. And then the algorithm was run first on this connected component, on this connected component. And indeed, they were placed on circles. And yeah, I mean, in this case, you would argue, well, I mean, why does it have to work on connected components? Because we can also place non-connected components on a circle. But the point is just to demonstrate this, that you can ask this. Now, I said there were also post-processing the framework does. So let's do something interesting. Add an option called orient right. So say this edge has the option it should go right. And indeed now, what the framework does is going to rotate this graph so that the edge from A to B now goes right. And notice that the algorithm didn't bother about that at all. It didn't even see that. Another thing we could do now, just to give you some examples. Here, let's add some options called stub. I was inspired by this other talk to turn this drawing into a stub drawing. Again, the algorithm won't notice because this is done by the higher layers of just rendering these edges in a certain way. And finally, here add lots and lots of other options, and then you get nodes with shadows and whatever. So the point is that the graph drawing algorithm doesn't have to worry about that. Your graph drawing algorithm is this. That's it. And all this other transformational stuff is going to be done by the framework. OK, so let me conclude. Graph drawing TeX is, on the one hand, aimed as users. Most of you people, presumably, want to draw a graph with, say, up to 100 nodes. Otherwise, you won't be able to fit it on a page inside a TeX document. And you just want to use it. On the other hand, it also addresses you as a researcher. If you have a new algorithm that you just want to try out, the idea is you have to write very little code that is then going to be usable in a wide variety of contexts automatically. You don't have to worry about anything else around that. To give you an impression what's there already, because a very new thing, we have essentially Weingart-Tilford for drawing trees. The whole layered Sugiyama method was implemented by a student of mine with it's configurable to death. And then we have multi-layered four-space algorithms that are also implemented, although they need some improvement in my opinion. If you want to use it, it's available as part of TICS itself. Currently the development version, you have to download this from SourceForge or check it out. But actually it's going to migrate to your computer sooner or later, because being part of TICS, it's going to be part of the next text distribution, and the next text distribution is going to be on your computer at some point. And that concludes my talk. Thank you very much.
Thank you very much, Till. I guess there are short questions. We won't have time for too many, but let's start with Walter.
Is it possible to call external procedure in Lua? Suppose that I have an algorithm implemented in C or C++.
Yeah, so in principle it's possible to call an external library because Lua allows that. The only reason why this is not yet implemented, it's not because it's so difficult, because it sort of breaks the idea that if you have this very simple demo load, you just give it to someone that can run it immediately. If you have a C code, what has to be compiled has to be distributed, targeted all the different platforms, so that's hard to do, and it's not as portable as this pure TICS version is. But other than that, yes, you can do this, but it would need some improvement. We've been discussing this and how to do this with OGDF, and in principle, yes. And certainly when it comes to things that are very time intensive, you should do that, I presume.
David?
Is it possible to run this on servers that expect to receive tech code from untrusted sources? Or does the use of Lua make, such as Archive?
Yeah.
Or does the use of Lua make this too insecure?
No, I don't think, because the whole tech thing usually runs in Sandbox. So you can configure tech how much you allow Lua to do, and by default a lot is switched off, so it won't be allowed to call other things. Let me phrase it this way: it's easy to configure Lua in such a way that you can run it very securely on any server you want.
The very last question, Ulrich.
Is there a way to reuse the result of the previous computation, like in make index, or do we have to, every time that you typeset, run the algorithm again?
So there are two answers to that. The one thing is what is already built into TICS is then when it sees a picture and the picture hasn't changed, then this externalization library is simply going to write it to a PDF and then reinsert it way quicker, so that works by default. But actually for graph drawing, what you'd really like, I think, is that you get a representation of the graph, and then the lower layer should notice, oh, I've seen this graph before, so I don't need to run the algorithm, I have a repository. That's not implemented yet, but you could do it. I mean, because my student said, this takes so long, I said, yeah, why don't you cache it? Oh, yes, good idea. So you could do it, but actually for this talk and also for the final version of the paper, I used this externalization library, which worked very well. Don't notice at all.
Okay, so there's a large lunch break after the session where you can discuss many more questions that you have. So let's now continue with the second talk. The speaker of the paper that was planned is unfortunately not here, but we have a wonderful replacement with Nishat. So please, we're now starting the point set part of this session.
Hello, I'm Nishat. I'm presenting the paper Kinetic and Stationary Point-Set Embeddability for Plane Graphs. This is a work by my colleagues at UVic, Zahid Rahmati, Sue Whitesides, and Valerie King. So we all know what a point-set embedding is on a stationary point set. So you have a set of points that do not move, and you have a graph, and you have to map the vertices of the graph on this point set and draw the edges in a way that no two edges cross. So we map the vertices here and then draw the edges. So that's an embedding of this plane graph. Now, what happens if the points move in a predictable trajectory? Like we assume that no three points are collinear in a positive interval of time, And we also can have the trajectory expressed as an algebraic function. Then what happens? That's the question that this paper asks and try to answer. So these are some related works. There are some works on kinetic proximity graphs, closest pair, Delaunay triangulations, Euclidean minimum spanning trees. These are the references: Gibas et al., Bash et al., Rahmadi et al., and Abam et al. Sorry. And we know some point-set embedding works by Kaufmann and Visa, by Bose et al., Di Giacomo, Cavallo, Beadle, and recently Durocher et al. But there has been no results merging these two branches. So this paper is the first try to merge kinetic data structure with point-set embeddability problem, and it introduces that data structure here and an algorithm for two-band point-set embedding. So the kinetic framework of this graph can be expressed like this. So for any 4 points at any given time, the point Pi should not be inside the any triangle created by 3 other points, and it should not create any crossings. So to maintain these properties, they define a set of certificates that certifies the validity of the point-set embedding or the mapping at any critical time. And a critical time is when an event occurs, so that we might have to change the mapping of the vertices to the points. So one example of such a certificate is shown here. So the certificate is at any given point, the point P3 is not inside the wedge P2. That is the wedge made by extending the edges P2, P1, and P2, P4. So we know that the point P3 is moving, and what happens when the point P3 moves inside the wedge? If it's inside the triangle and there is no crossing yet, then we change the mapping like this. So now P2 is mapped to P2, and P4 is mapped to P3, and we change the edges like this. And now we also have to remove this certificate and insert a new certificate that says that P2 is not inside the wedge P1. So the same thing goes for this case when P3 is not inside the triangle, but it moves into the wedge and creates a crossing. Then again, you change the mapping and form a new certificate. Okay. So how do we measure the performance of a kinetic data structure? There are some standard measures. A data structure can be efficient, responsive, compact, and local. So the efficiency means it's the ratio between internal events and external events. So internal events are events when the target attribute is not changed. That means the mapping does not have to change. And an external event always changes the mapping. So you have more external events, then it's a good thing. And also the responsiveness means the processing time of each event, and the compactness is the size, and the locality shows that when there is a change in some mapping, you don't have to change the whole thing. You can just make some changes locally, and that keeps the certificates valid. So first, we talk about the three-band drawing algorithm. In this algorithm, it's on stationary point set now, but later we'll show that how you can convert this algorithm to an algorithm that keeps the embedding valid over time when the points move. So first, you have to order the points according to their x coordinates. So P1, P2 up to P12. And then take the graph and find a Hamiltonian cycle here where at least one edge has to be an outer edge. So actually what they are doing, they're taking the algorithm of Kaufmann and Glisse, but they're making a slight change which does not improve the bound given by Giacomo at all, but this change help us to keep the embedding intact or keep the valid embedding on the moving point sets. So to get the Hamiltonian cycle, we need some dummy vertices like V1 and V6. This edge has been subdivided once by the dummy vertex Z1, and then we add the edges Z1, V8 and Z1, V7. Next, what we do, we map the vertices V1, V2, V3 on the Hamiltonian path on the point set, and when there is a dummy vertex between here 10 and 11, we have to take the middle point of the line segment P10 and P11 and insert a dummy point there so that we can map the dummy vertex. So here's the Hamiltonian path. And the next thing is you have all the internal edges that is inside the cycle and the external edges that is outside the circle. And you put the internal edges above the chain and map the external vertices, edges below the chain. And you have a band for each edge. So the difference in this algorithm is assigning the slopes here. So for each edge, you assign the slope this and this for the two segments. So one is 1 plus d over n plus m delta, and the other one is minus 1 plus d over n plus m delta. And where d is the distance between the points. So for example, P1 and P9 has distance 9 because there is a dummy vertex in between. And m is the number of total dummy vertices, n is the number of vertices, and delta t is the maximum slope of the consecutive edges on the cycle, on the Hamiltonian path, that is shown by the bold chain over there. So this delta is a function of time, so it changes over time when the points are moving. So how can we keep track of the maximum slope? That's why we need these dynamic and kinetic trigonometry. So all the leaves contain the slope of each edge on the chain, and it's a binary tree, so the parent gets the maximum of these two, so the root has the maximum of all the slopes. And why do we need the tree? Because we know that the slopes are going to change, and sometimes we have to remove some slopes and insert new slopes. For example, in an order event. So an order event occurs when the relative position of 2 points changes. So suppose at time t minus qi was to the left of qj, and at some point qj came to the left of qi. So now there are lots of crossings. So what do we have to do? We have to change the mappings. So the vertex that was mapped on qi is not now mapped on qj, and the vertex that was mapped on qj is now mapped on qi. And we change the incident edges, and we remove the previous slopes. So here we have to remove this edge, this edge, this edge. So we remove those slopes from the trigonometry, and then we insert 3 new slopes and change the tree structure. Now we have the 3-band drawing, and using the dynamic and kinetic trigonometry, you can keep the embedding plane when the points are moving. But what about getting a 2-band drawing from the 3-band drawing? So you get the 3rd band when you have a dummy vertex. So if you draw an edge from there to there, you just go 1 band, 2 band, and 3 band. So we want to save a band by drawing these 2 segments on a straight line, a vertical straight line, so that we have only 2 band at most. So you see that we changed the two line segments into one vertical line segment, but that creates some crossings. So we have to rearrange the slopes or need a way to calculate the slope so that there are no crossings there. For that, we need a nested tree. So what is the tree? That's also on the edges. So I think I forgot to mention that this is always a triangulated graph. So the leaves of the tree would be the edges where the endpoints has distance 2. And it's a binary tree because it's a triangulated graph, so each internal node would have at most 2 children. And we draw the tree like this. Now in this tree, for each edge, we store 2 values, one for the left slope and one for the right slope. So if both the endpoints are not dummy vertices, then we just point delta and minus delta. Just to remind you, delta is the maximum slope on this chain. So that's the same for this one, but for that one, we can put delta and minus delta because the right end is a dummy vertex. So what we do, we draw a vertical line there and extend this segment so that it intersects. Then the parent of this node, we get the right, in this case, the right end, and connect with the intersecting point. And the slope of this line is alpha. So for the right segment, anything that goes to the right of Q7, the slope has to be at least alpha, minus alpha. So we store delta and minus alpha here. And when we go to the internal node, for the left value, we take all the values and pick up the maximum. And for the right value, we take the absolute values of all the children, the right values, absolute values, and take the negative of that. So it's delta minus delta for that, but delta minus alpha there. And for the root node, it's delta and minus of maximum alpha and delta. So once we have this tree all constructed, we just assign slopes like this. So for this one, it's a 1 plus 2 over 8 delta. 8 is the total number of vertices, including the dummy vertices, and the distance is 2. And we assign slopes like this. Here, the left slope is 1 plus 2 over 8 delta, but the right slope is just infinity. And it goes on like this, like that, and that's the two-band drawing of the graph. So if we analyze the performance of this data structure, for the three-band drawing, it uses linear size, and for the two-band drawing, the tree uses linear size 2. So both of the data structure in both algorithms are compact, but in the first case, in three-band drawing, the algorithm processes total this number of events. That's a very big figure, and each event is processed in order of log square n times. So that's responsive and efficient and local. But for the two-band drawing, we can't maintain all those properties. So it's only compact, but it's not very efficient, not very responsive, and not local. So for a slight change, you might have to change the whole graph embedding. And for future work, as we have already shown, that the data structure for the second algorithm is not as we wanted. So we would like a data structure that satisfies all the standard performance criteria. And also, we did two-band drawings, two-band poinset embeddings. So it would be nice if we could do the same thing for straight line drawings on moving pointsets. Thank you. If you have any questions, I would be happy to answer if I can.
Thank you. Wonderful. Not being an author and giving such a good talk. Wow.
I practice.
Are there any questions?
Okay.
I mean, in the algorithm for two beds, in the stationary case, you have in the Kaufmann in this algorithm, you need the rotation to avoid the point.
Yes.
But there is a paper by Beppe
Yeah.
where you don't need the rotation. I mean, you
Yeah,
get
you
two
don't.
beds for free.
Yes.
Can you use it, that approach here, or there is something that doesn't work?
I think you can use it, but just to maintain the tree, I mean, when the points are moving, I think this is much easier. I think, yeah, I saw the paper, and I think that can be used, but just for my opinion, I think using just keeping track of the slopes and assigning the slopes when the points are moving, just recalculating the slopes of all the edges, that is easier. Just. Any other questions? Oh, yeah.
Yeah, so have you considered, or is it difficult to consider a colored version of the problem, where some of the vertices have a color and some of the points have the same color?
I don't know if they have thought about it, so I'll relay your suggestion to them. That's a very interesting problem.
And I think it's the perfect transformation to the next paper, which exactly deals with colored point sets. Thank you again.
Thank you very much. I'll be talking today about some work on color point sets to answer Beppe's question. Well poised, since he's one of the co-authors here. This is work with Fabrizio, Mark Glisse, Beppe, Tamara, and Nishat. This work was begun at the most recent INRIA McGill Victoria workshop on problems in computational geometry. So I'd also like to thank Sue Whitesides and Sylvain Lazare for organizing that and inviting us down. Sadly, we don't have any moving point sets, at least not intentionally moving point sets, but as a bonus, you will see many examples of the consequences of not having your graph drawing system well integrated with your typesetting system. So you can look forward to that. So here's an outline of the talk. I'll set up the problem, which will take no time because you now all know what graph point set embeddability is. Talk briefly about some previous work, outline our results, and then hope to focus a little bit on some of the highlights of some of the proofs, and end with some open problems. So there's a graph, there's a point set, there's some drawing constraints, and there's done. That's graph point set embeddability. So there's been a lot of work in this area. A lot of theorems have the following form. You give me some classic graphs, you give me some kind of constraint on your point set, like maybe it's convex, or maybe they're in general position, some drawing conventions, and then you try to say something interesting. And many people have succeeded at this game. Results on outer planar graphs, NP completeness results on planar graphs, NP completeness on planar graphs with bends. So that's the basic game. But then you can have variants of the basic game, and one is with respect to universal point sets. So here you have a class of graphs, and you look at all the graphs in that class that have a fixed size, n vertices, and you want to find a set of points upon which you can embed all of the graphs of that size. And of course, there's been work done here too. Oh, I guess it's easy. For planar graphs, you can draw them on a 2n-4 by n-2 grid, and you can do it efficiently. That was later improved to a slightly smaller grid and a slightly faster algorithm. So that's one variant, and we'll come back to that later in the talk. Another variant is to try to constrain the assignment of the vertices to the points in the point set. And so one version of this is called embeddability with mapping. So now you add a bijection of the vertex set to the point set, and you try to get an embedding onto the point set that respects the bijection. So boom, boom, boom. And one of the better known results here has to do with planar graphs, arbitrary point sets, and drawing polyline embeddings that don't have too many bends per edge, and that can be done efficiently. Well, if you don't want to constrain your drawing too dramatically, you can instead color the vertices of the graph, color the points in the point set, do this in sort of a compatible way so that if you have 17 red vertices, you have 17 red points, so that at least you have a chance of respecting the coloring. And then ask if you can embed so that the color classes are preserved. Graph, point set, embedding, and kind of well-known result there. K-colored planar graphs. You can do this with a polyline embedding so that you don't have too many bends per edge. Okay? So that's some of the background. In our work, we focused on trees. We focused on two-colored trees. And in this case, it looks like it's a properly two-colored tree, but they won't always be. And you have a two-colored point set you want to embed. So we call this a bichromatic embedding if you respect the coloring of the graph in the point set. Sometimes it can be hard, even for what seems like a very easy problem. So here we have a properly two-colored tree. We have a convex point set, and we want to embed. And it turns out that that problem ends up being NP-complete. So if you try to make it easier, you can further constrain the point set. So if you require that the point set not only be convex but alternating in color, then it finally becomes easy. You can determine in linear time whether there's such an embedding. Okay? So those are two of the results on embedding trees into convex point sets. Then we looked at universal point sets. We wanted to find bounds for the size of the smallest two-colored point set P that would be universal for all bichromatic straight line embeddings of all n-vertex two-colored graphs. And we got an upper bound that's a pretty simple result. You might think about it for fun if your mind starts to wander in the next few minutes. We have a lower bound that's a little more interesting. We can show that any such universal point set will have to have at least 3 halves n vertices minus a little bit. You could probably quantify that a little bit, but we were a little lazy. So that's the last slide in a nutshell. If the tree is properly colored, then in fact you can improve the bounds a little bit. You can get lower bound 7n over 6 minus log of n, and upper bound of 4n over 3. Okay? So that's some information on universal point sets. And finally, we looked a little bit at polyline planar embeddings. And what we did is we looked at point sets that were linearly separable. And we were able to show that if you have a two-colored tree and a compatibly two-colored, remember compatibly just means the colors add up properly, planar point set that is linearly separable, then you can do a one-bed bichromatic embedding on that point set. So those are the results. And what I'd like to do with my remaining time is look at a few of the highlights of some of those. OK, so we need a little bit of notation and 1 or 2 known facts. So all we really care about on this slide is this tree on the left and the numbers that are labeled on the vertices. So the idea behind these numberings, the label on the vertex, and think of this as a rooted tree for now, is called the surplus of the vertex. And it's basically trying to tell you by how much the color of the root node is winning over the other color. So if you look at this tree, there's 1 more red node than blue node, so this gets a 1. Of course, leaves all get 1s because they only have 1 node and their color wins. If you look up here, this blue node got a -1 because it's actually running a deficit color-wise with respect to its subtree. This subtree is nicely balanced. So a rooted tree is called balanced if none of these numbers are too big, if they're all between -1 and 1. Okay? And a tree is called color balanced if you can pick it up by some vertex and make that the root, and it's balanced from the point of view of that root. Okay? So we're going to be thinking about these balanced trees a little bit. Another fact that's useful to know is that if you have a straight line embedding of your tree on a convex point set, and you look at the subtrees you get by deleting a vertex of your tree, then the subtrees that are remaining are all mapped to consecutive points of the point set. So there's one of the subtrees, there's another one, there's another one, there's a tiny one. Okay? So we need those 2 facts. All right. So I'd like to give you an idea behind the proof of the following theorem. This says that any properly 2-colored tree can be embedded on a convex alternating point set if and only if the tree is color balanced, our previous definition. And you can check that color balance property pretty quickly. And I want to talk about why color balanced implies embeddable. And the idea here is pretty simple. What you want to do is you want to take your tree, root it at a vertex where it's going to be color balanced, and then kind of from the bottom up, build a 1-page book embedding of that tree that has some properties. And I can list the properties for you. Boom, 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 boom. But it's probably better to look at them on the next slide. So basically, when I look at my tree V and I look at its subtrees, each of which has some root, they're going to fall into 3 categories. Either the root has surplus 1, so it's got 1 more blue than red in this case, so it's going to alternate. And what we want to make sure is that when we embed it with the one-page embedding, the root can see up to infinity, so there's no edge crossing over it. Here's another possibility. The root had surplus 0, same number of reds and blues. And here's the third possibility where it had surplus -1. So from these building blocks, we just want to be able to add V to the one-page book embedding, and it's not surprisingly pretty easy. What you do is you first note that you're going to have the same number of type C1 trees, that is ones with a blue surplus, as trees with a red surplus, because after you removed V, since V had surplus 1, you have the same number of red and blue vertices in all those subtrees. And so you're going to have the same number of class 1s as class 3s, and all you really have to do is alternate class 1, class 3, class 1, class 3, and then throw on all your class 2s at the end, and then put V on the left and attach it like that. So you can build up the graph that way. Okay. So that's one of the problems where determining the embedding is actually pretty easy. Now, if you just drop the alternating constraint from the theorem, then all of a sudden it becomes a much harder problem. So properly two-colored tree, just a convex point set, it becomes difficult. And the idea here is that you're going to reduce the problem to a special form of three partition. So let me just quickly remind you what three partition is. You're given an integer b, positive integer b, a set A of positive integers. There are 3m of them, a multiple of 3 of them. And your goal is to construct disjoint point sets, disjoint 3 sets from the set A, each of which has its elements summed to b. And the fact we appreciate about this problem is that it's strongly NP hard, so that even if b is bounded with respect to the size of the elements of A, and in fact even if each of the a's are even, this is still an NP complete problem. So what we want to do is take an instance of this version of three partition, build a tree, build a point set, and show that embedding the tree onto the point set means that you can satisfy this three partition problem. Okay? So here's how we do it. For each element A, we have an alternating path of length A sub I, so length A sub 1, length A sub 2, and so forth, attached to a root. We then have a bunch of trees that are going to help anchor other parts of the tree. So these M trees over here, we call them star trees. The names are not very creative. Send suggestions if you have better ones. And there's a special tree over here that's going to anchor the root. This value A is just the maximum value that any of the elements of the set A takes on. So you need these to be large enough that they can do the job of anchoring the tree into the point set that we're going to build. Okay? And in the point set, the goal will be to have these paths cluster in groups of 3 on the point set, and they're going to cluster into bins of size b, so that means each set of 3 numbers will add up to b. Right? So there's the point set. The root's going to go there if we're lucky. You can see right here, that was that rightmost red star tree, we called it, that's going to let us anchor the root where we want it to be. This is an example of a bin. It has B alternating red and blue points. And this is one of those M star subsets that separates a bin from the next bin. And these just go around like that over to there. Okay? And as it turns out, if the three partition case is satisfiable, these paths will nicely fall into the bins. And the root will fall there, and everything will work out lovely. And if, in fact, you can embed this onto this point set at all in a planar straight line way, then, again, it'll embed so that 3 paths are in each bin. That completes the little outline of the proof sketch. Finally, I wanted to talk a little bit about universal point sets for one-bend embeddings. So here the idea is we're given a two-color tree, and we're given a two-colored point set, and the only thing we ask for our point set is that it be linearly separable, so there's a line with all the reds on one side and all the blues on the other. And if that's the case, then we can embed the tree onto P with at most 1 bend per edge. Okay, so let me give you a sense of how that goes. Two-step process. The first step is we transform the problem into a 2-page book embedding problem. And then we show you how to embed your tree onto that as a 2-page book embedding. All right? This uses a result of the Giacomo, Liotta, and Tratta, And the result is the following. G has a bichromatic one-band embedding on P. That's just what we're looking for. If and only if there's some line, L, such that G admits a bichromatic two-page book embedding and then some stuff in red. So the stuff in red, consistent with sigma LP. Well, sigma LP is an ordering that the line L imposes on the points in your point set. And so you just want the bichromatic two-page book embedding to be consistent with that ordering. And so here's, by way of example, here's a point set. There's the line. Project orthogonally down. That gives you an ordering on the points. And so you just want G to have a bichromatic two-page book embedding that has that pattern of colored points. Okay? So that's what we're going to aim to do. Right? And the way we do that is we take our point set, which is fortunately linearly separable. We take an appropriate separating line so that when I look at the perpendicular bisector, the points project nicely down onto it. Just nicely meaning no two points end up in the same place. And you'll notice that what will happen in this case, you'll have all the reds on one side of this portion of the line and all the blues on the other. And so what we're going to do is show you how to embed your two-colored tree on something that looks kind of like that. Fine. Great, thanks. And I just thought I'd walk you through an example. So there's a tree, two-colored. The idea here is that we draw it onto that point set top-down, kind of one level of monochromatic trees at a time. So first we'll draw that red tree onto our spine. Then we'll draw those blue trees. Then we'll draw those red trees. Then we'll draw those blue trees. So you can watch it happen. We start over with the red tree. You can see it over there. And then we sneak down the bottom page. And then we draw the blue subtrees. And then we jump over the top page. We draw the red ones. And it's really pretty just that easy. Okay, so that's a flavor of some of the ideas that were involved in the proofs of the results. There are, countably infinitely many problems of this type, at least. And here are 3 chosen not quite at random. If you think back to those decidability results, we're still looking for like the easiest hard problem, right? And so one candidate for that would be assume that your two-colored tree is a binary tree and that your point set P is convex. In that case, is it fast or is it still NP complete like it was for the non-binary trees? We don't know. Can the bounds on the sizes of the universal convex point sets be tightened? I think there's a good chance they can be. And what if you don't constrain the point sets quite so much? So convex is a pretty heavy constraint. You could say they're in general position. You could say that they form 2 or some finite number of convex curves. But we know very little about this. So those are some of the problems that we've thought about. These are some we'd like to think about. And thanks for listening.
Thank you. There's time for a couple of questions.
Or not.
Yeah, go on. Joe.
So if you can go back, I'm just curious, you described the 2 book embedding, and then you gave linearly separable points, the red and blue points. But how does this, so how do you go from the book embedding here to the embedding it onto that?
The original point set?
Yeah.
Oh, yeah. So you appeal to the theorem that I mentioned here. That says if you have such a book embedding, you can do it. You can thank the man behind you for that result. Any other questions?
Okay.
Great.
Thank you.
So thanks for the preparation, explaining everything about colored point sets. I'm going to talk about a monochromatic problem for points and graphs through it, but the motivation comes from a bicolored point set from a paper by Fülek, Kesseg, Moric, and Wilrich. So they wanted to separate the red and blue points in a bicolored point set by a simple polygon. And they could prove that if there are, let's see how it works. Oh, not this one. Oh, it's a separate one. So
if there are far more blue points in the interior of the convex hull of the red points, then it's possible to separate them using only vertices of the blue point set. And they conjecture actually that way fewer than r to the 4 blue points would suffice. So they conjecture that 2r minus 1 would be enough, but they don't know. For separating the points in a different way, they also had this result that if they're exactly the same number of blue and red points, then one can use 3.5 vertices for separating the red and blue. If the separating polygon doesn't have to, can use Steiner points. And what they do is just add wedges to the convex hull incisions, and to add any such new wedge, they have to use 3 additional vertices. But these points are Steiner points, right? So this led them to this question that Philip Moritz posed that 2 years ago, that if you are given now a monochromatic point set, what is the fewest number of segments in a pass, a covering pass that goes through all the points? So if you have a monochromatic point set like here, you would like to have a pass that visits all of them. The turning points don't have to be in the point set. And of course, if you think about the motivation, a crossing pass would not be really what they are interested in. They would want a non-crossing pass, and that's their other question, that what is the smallest number of segments that can do this for m points with a non-crossing pass. And so if the best possible bound for this is n.5, if the points are in general position, then a segment can't cover more than 2 points. And if you can always cover 2 points with such a pass, then their previous bound on separating red and blue points could improve to just n, because such a pass could be thickened to a small channel where every vertex here would yield 2 vertices of the separating polygon. So that's the connection. And here comes our work, where we gave some bounds for these 2 questions. But let me just mention another motivation, the obvious connection to the traveling salesman problem. In a classical traveling salesman problem, you have given monochromatic points, and you want the shortest tour that visits all of them. And of course, it's NP-hard, even a geometric version, and there's a p-task for it. But it has also many variants, because it's such a classical problem. These are typically called angle TSPs, where you still want to visit all the points, but you want to optimize some other constraint, not the total Euclidean length. So such constraints could be the minimum number of links, minimum number of segments in the tour. This is also known to be NP-hard, and so this has been studied 10 years ago already. And there are more variants where you want to minimize the minimum, maximum turns in a Hamiltonian tour, or you have an angle constraint that a tour cannot turn by more than an angle alpha, and you still want to minimize the total length. So I'm not going to talk about any of these variants of TSP. I'm talking about covering paths again, and the corresponding version of TSP is just the minimum length covering path problem that asks for a polygonal path that goes through all the points. The vertices could be anywhere in the plane, don't have to be in those points. So this is NP-hard. It has been, there are some approximation algorithm, and for which a variant that has been studied a lot is the axis parallel version, where either you're interested in visiting all points in a grid, 2 or 3 or d-dimensional grid. And the question is, what is the minimum number of turns that are necessary? Of course, the number of turns corresponds to the number of segments. And this variant here is, asks the minimum number of turns for an arbitrary point set, not a grid. And so for this, there are fairly close bounds. So let's get back to the problem I'm going to talk about. So we are given a set of points in the plane, and we want to cover them with a path that can turn anywhere. And we are interested in the minimum number of segments, and for an arbitrary path and for a non-crossing path. So as I mentioned, the n-half lower bound is trivial because a segment can cover at most 2 points at a time. And here we proved that it's pretty close to the truth if we don't care about crossings. Don't worry about crossings. You can so this is something that we very quickly observed with Adrian and Dumitrescu after the question was posed, and since then other people also find the same result. It's based on the Erdős-Szekeres theorem. It's a simple reduction. I'm gonna show you anyways. And the other variant, the non-crossing covering path, is much harder. It's hard to say anything about this non-crossing constraint. A lot of people tried to give upper and lower bounds since in the last 2 years, since the problem was posed. This is the first non-trivial lower bound, something bigger than n-half. And I will mention at the end that the upper bound also has been improved just very recently. So the 2 results are the upper bound, where we can construct an actual covering path that is not much longer than n-half, and for the non-crossing version, we have a point set, a construction that requires a long covering path. So let me show these 2 results just briefly. So as I mentioned, it's based on the Erdős-Szekeres theorem, which says that every set of n points contains a subset of at least log n points in convex position. But the proof actually uses is not points in convex position. They use very special points in convex position, caps and cups. They have a recursion for those. So a cap is just, or a cup on the left is a set of points where there's an x monotone curve and that going through all of them, and cap is the concave curve. So an obvious observation here is that if this is your point set, then of course you can just draw segments to pairs of them and align them on a covering path. So n-half ceiling segments will be sufficient. So the Erdős-Szekeres theorem actually have a bound for exactly caps and cups, not for convex sets. And I also want to point out that this obvious observation is actually not true for points in convex position, because one could, so one could not necessarily continue the these 2 paths. If for instance, a cap and a cap is odd and a cup is also odd, then we could not glue them together. But for caps and cups, it works very nicely. So and also there are algorithms. So Erdős-Szekeres is a very classical result. There are dynamic programming approach algorithms to compute a maximal cap or cup. So with this observation, it's easy to construct a covering path. So once we have n points in the plane, we can just pick out caps, maximum caps and cups independently and remove them. until the number of points drops below n over log n, and then we stop. Now, for every cap and cup, we have an optimal covering path, just for k points, k half, ceiling. We might lose 1. And then for the remainder points that we don't really care, there are few of them, we can just have a Hamiltonian path, and then link them together at the end. So in pictures, this is how it would look like. If you have a point set, we pick out caps and cups greedily, and then the remaining points are connected by some path, and they are linked together. So what is the other result? So let me stop for a remark here. The idea was to have a path that a subset for which we have an optimal covering path. So Emmo Welzel asked the question that if we don't really care about caps and cups, we just want these type of subsets that for which there's an optimal covering path, what can we say? So he called these sets perfect. So set of points is perfect if there is really a covering path for them that where every single segment covers exactly 2 points. I should add that points are in general position. Otherwise, it's not that it leads to something else. So he asked, what is the largest integer, p of n, that every set of n points in general position contains a perfect set of this size. So the Erdős-Szekler's theorem gives a lower bound of log n, and that's the lowest. That's the best lower bound we have. This function could be anywhere between n and log n. All right. So let's go back to the continue with the non-crossing version, where we have a construction for a point set for which every covering path will have more than n½ segments. So it's a constant factor is bigger than 1/2. So this is a point set with twins. So there are points A and points B. The points A are on a parabola, and the points B are really close to the first points. They are twins. That's how we call them. And they have a bunch of properties, so that I'm going to list them one after the other. One is that the lines to the twins are almost vertical, not completely, because we want general position. And any two of them meet somewhere below the parabola. So this property just guarantees that we cannot just zigzag through all the twins in some order. That will definitely not be a covering path. So maybe we can zigzag through one, going down and come back, but then we cannot continue with another such segment. Okay? And then the distances between the twin pairs increase very rapidly, exponentially in I. So I even have to tell you how exactly. So if you just have two consecutive pairs, so first of all, so for the last one to the rightmost pair, we just put BK a distance delta above AK, where delta is some small neighborhood. And then we choose the distances in reverse order, recursively. So once we have already BI and AI, then we choose the next. Sorry, if you have AI plus 1 and BI plus 1, so here we already have this pair, then we can choose the location for BI. So BI should be much closer to AI than the distance here. And it should be so much closer that if we connect the A points and the B points, then the intersection points of these two almost parallel, seemingly parallel segments should be inside this small delta neighborhood. So this is always possible. We can just go closer to AI than the distance was before, and the distance will decrease exponentially. And this is enough. This is all we need for the construction. So this property, we define it for consecutive pairs, but of course it carries over also. Yeah, well, not all, yeah. If you are careful enough or not very lazy, then it easily carries over to other pairs. So this will be true for any pairs, not just consecutive ones. Okay, and then once you have these points that we want to say something about the covering path. So let's take an arbitrary covering path, and it has two types of segments. Either a segment is perfect if it covers two points, that's the best it can do, or it's imperfect. Of course, we want to say something about that. Most segments are, or many segments are not perfect. So how could a segment be perfect? One option is to cover a twin. Then this segment will be almost vertical, and because of this property of these almost vertical segments, the top vertex of this segment will not be incident to another perfect segment. So it either the path continues with an imperfect segment, or it's just the endpoint of the covering path. Either one is good for us. So the more interesting case is the other type of perfect segment, where perfect segment covers one point from two different twins. Where, for instance, EI is the smaller one. And then the intuition is that this segment will go very close it will miss 1 point from each twin, and the second point from the left twin will be very difficult to cover. So a covering path will have to cover in some way this other point as well, but it has to be very close to the covering path, and to avoid crossings, it either has to turn somewhere in this small neighborhood, or it has to go almost parallel to the first segment, and then it has to miss something. So we examine this case very carefully, and these are the possible ways that this second point can be visited if one of the points is covered by the perfect segment. And so I'm not going to go through all these cases, but we conclude from this is a charging scheme that we can conclude that we conclude an upper bound on the number of perfect segments. We show that there can't be 4 times more perfect segments than non-perfect segments. Essentially, we charge every perfect segment to one of the endpoints of an imperfect segment. And then we make sure that every such point is charged at most twice. And that gives this factor of 2. So we have, if we combine this inequality, so upper bound on the number of perfect segments, with just a bound that every perfect segment covers 2 points, and any imperfect segment covers just 1 or 0. There's a parameter for 0, 2. Then the total number of segments is at least 5/9 times n, roughly. So that's our bound. Let me note here that we don't have a tight analysis even for this point set. So we have we prove a lower bound for a covering path for this particular point set, and we know that it cannot go all the way to n. This point set does have a covering path with 5/8 segments, but we don't know what is the lowest number. And of course, we don't know what is the answer for the question, what is the value of g of n. So let me remark that here that we proved the lower bound for the non-crossing version. And this year, Daniel Gerbner and Balázs Keszek proved that the upper bound is a little bit less than n. So they proved that for some positive epsilon, it's at most 1 minus epsilon times n. And let me finish with another problem that for the motivating problem of separating red and blue points, Actually, it was not really important that the points are covered by a pass. A tree instead of a pass would be just as good, would give just the same kind of improvement. So Balázs has asked the same question for trees as well. So this would be a covering tree for the point set. Intuitively, one could have fewer segments than for pass, but the bounds are not better. The currently known bounds are not better for trees than pass. So I stop here.
Thank you very much. Are there any questions? Please.
Can the problem make sense if instead of the segments you count the number of slopes?
Yes. Then the general position assumption would not make sense. So that would be probably a different type of problem where you need to exploit how degenerate the point set is. I think.
Any further questions? If this is not the case, let's thank all the speakers of this session again.